Chapter 19, Weather Patterns and Severe Storms. Air masses. Characteristics of large body of air. If the large body of air is 1,000 miles or more across and possibly several kilometers thick, we'll categorize it as a large body of air or air mass. It has a similar temperature at any given altitude, similar moisture at any given altitude, and moves and affects a large portion of a continent. Okay, so a Canadian cold air mass. Okay, it may be very cold. So in this example, it's minus 46 degrees Celsius, and as it travels down, it may travel down into the United States, bringing with it very, very cold winter weather. Air mass is a source region, the area where an air mass acquires its properties. Like I just mentioned, the Canadian cold air mass. Well, it originated in Canada, so that's why we call it Canadian cold air mass. Two criteria used to classify air masses: by the latitude of the source region, so polar or P is a high latitude cold. If it's tropical, it's a T, a low latitude warm. If it's continental, C, it forms over land and it's very likely to be dry. Then maritime is an M and it forms over water, it's humid air. Okay. So a continental polar air mass is a CP. A continental tropical is a CT. So these are drier but cold and warm. Maritime polar, MP, humid cold air. Maritime tropical, humid warm air. Okay, so here's our major air masses based on the source region. So here we have our continental polar, Canada. Here's our continental Arctic, it's very, very cold, dry. Our marine polar, cool and humid. Over here, marine polar, cool and humid. Then our marine tropical, warm and humid, and our marine tropical, warm and humid air. Okay, that's the winter pattern. Then in summer, we lose that continental Arctic. We just have a CP and our MPs and our MTs. And our MTs kind of expand. They cover all the Caribbean across this whole zone where we usually watch for hurricanes coming to Florida. The maritime tropical kind of take over this region. The CP and MT air masses are the most important air masses in North America, especially east of the Rockies. Continental polar air from northern Canada and the interior of Alaska in the winter bring cool, dry air, and the summer brings cool relief. Continental, it's also responsible for lake effect snows. The CP air masses cross the Great Lakes. Air picks up moisture from the lakes, and snow occurs on leeward shores of lakes. So when that that cold, moist air hits the land, it'll drop out snow on, let's say, for example, Buffalo, New York. Okay, so here's our diagram. Here's the Great Lakes. Okay, that cold air mass comes through. If it travels across the lakes, it'll pick up a lot of moisture, and then it'll dump snow here. It'll dump snow here. It'll dump snow here. When it goes across Lake Ontario and Lake Erie, so here it will dump a lot of snow here and a lot of snow here. Maritime tropical, MT, from the Gulf of Mexico and the Atlantic Ocean, warm, moist, unstable air, brings precipitation to the eastern United States. The continental tropical, CT, is southwest of Mexico, hot, dry, seldom important outside its source region. The maritime polar brings precipitation to the western mountains. Occasional influence in the northeastern United States causes a nor'easter in New England with its cold temperatures and snow. Fronts. Those are the boundaries that separate air masses of different densities. Air masses retain their identities. Warmer, less dense air is forced aloft, forced up, and cooler, denser air acts as a wedge and stays low. Warm fronts. Warm air replaces cooler air, as shown on a map by a line with semicircles and small slope. Clouds become lower as the front nears. It's a slow rate of advance. Light to moderate precipitation. So here's our warm front. So a nice low slope. The warm air is advancing and is replacing the cool air, and you'll have moderate precipitation, a lot of cloud coverage. A cold front, the cold air replaces the warm air, shown on a map of a line with triangles. The steep front advances faster than a warm front. Associated weather is more violent than a warm front. So the intensity of precipitation is greater, duration of precipitation is shorter, so we find more thunderstorm activity. The weather behind the front and the cold front is dominated by the cold air mass, subsiding air, and clearing conditions. So here we have our cold front coming through, and as it comes through, let's see our cold front line with our triangles, and it's a steep slope. So as the cold front is replacing the warm front, it's pushing that warm air aloft. Large cumulonimbus thunderstorm clouds may form and have heavy precipitation and lightning. But once the storm passes, nice cool air, the air is nice and cool. Stationary front. Flow of air on both sides of the front is almost parallel to the line of the front. Surface position of the front does not move. On a occluded front, active cold front overtakes the warm front. Remember, the cold front travels faster than a warm front. So when cold front overtakes the warm front, the cold air wedges the warm air upward. The weather is often complex, so maybe cloudiness, there may be rain, maybe some thunderstorms, and that precipitation happens because the warm air is being forced aloft. So as we start cooling, it'll drop out its water vapor. So here we have a cold front trying to catch up to a warm front. Eventually, as it collides, becomes occluded. That you have a lot of rain, heavy rain, and the warm air starts being pushed up. As the cold air overtakes that warm front, then the rain will lighten up a bit. Mid-latitude cyclones. Okay, primary weather producer in the mid-latitude. So we're talking in the United States north of Florida here. Okay, the life cycle forms along a front where air masses are moving parallel to the front in opposite directions. So if our continental polar air is often north of the front, and the maritime tropical is often south of the front. The frontal surface takes on wave shape with low pressure centered at the apex of the wave. The flow of air is counterclockwise, cyclonic circulation. A warm front and a cold front form the arms in a clock. And the cold front catches up to the warm front, produces an occlusion, the warm sector is displaced aloft, and the pressure gradient then weakens and the fronts dissipate. Okay, so we have the two air masses. Okay, so right here we have our cool polar and our maritime tropical under here. So we have our fronts developing, okay, and then a wave will start to form. And eventually our cold front and our warm front separates out. The cold front's will be moving faster than the warm front. So here we got that wave, and then we have a cold front and our warm front. Cold front is catching up to the warm front, starts occluding, okay, lifting up that warm air aloft. When it dissipates with its rainfall, dissipates, and the clouds are dissipating, that whole front falls apart. So these mid-latitude cyclones move eastward across the United States. The first sign of approach are in the western sky. It requires 2 to 4 days to pass over a region. The largest weather contrasts occur in the spring. Changes in weather associated with the passage of a mid-latitude cyclone. The change depends on the path of the storm. Okay. So with the warm front, the clouds become lower and thicker. There's light precipitation. After passage of a warm front, the winds become more southerly and temperatures warm up. Cold front, a wall of dark clouds, heavy precipitation, hail, maybe tornadoes. After passage of a cold front, winds become northerly, skies clear, and temperatures drop. Okay. So here's more of the cloud patterns. Over the cold front, you'll have your thunderstorms. Warm air will have those nimbus stratus clouds. Satellite view of a cyclone over eastern United States. The cyclones, so the cyclones and anticyclones are generated by upper-level airflow, maintained by upper-level airflow, and typically are found adjacent to one another. The cyclones, remember, is a low-pressure system, surface convergence, and an outflow of a lot of divergent aloft sustains low pressure. Anticyclone is a high-pressure system associated with cyclones, surface divergence, and convergence aloft. Okay, thunderstorms, severe weather types now. So first, thunderstorms. The features are with cumulonimbus clouds with heavy rainfall, lightning, and occasional hail. This occurs, there are probably about 2,000 thunderstorms at any one time in the United States. We have about 100,000 of them per year in the United States. We think they were all here in Florida, but basically they are most frequent in Florida and eastern Gulf Coast region. Okay, this average number of days per year with thunderstorms. Okay, in Florida, where we are, we've got 80 days, 360 we have thunderstorms. Some parts of the country have very little, like they have maybe only 5 here in California on average per year. Okay, stages of development. All thunderstorms require warm air, moist air, and a lot of instability. They are wanting to rise. So high surface temperatures, so the ground surface is high, most common in the afternoons and early evening. Okay? This requires continuous supply of warm air and moisture. Each surge of warm air and moisture causes the air to rise higher. Drafts and downdrafts start to form, so cycling starts to happen in the cloud. Eventually precipitation forms, the most active stage. Gusty winds, lightning, possibly hail, and very heavy precipitation. A cooling effect of the precipitation marks the end of the thunderstorm activity. Here's a picture of lightning. Okay, so here's our stages. We have this warm air. We got buildings here, so this urbanized area, a lot of impervious area. They heat up a little quicker than land around it, so we got this instability of differential heating. So this warm, moist air starts rising up. Okay, clouds start to form. Eventually form enough that we start entering these updrafts and downdrafts, which will start forming those. Possibly there's going to be hail or large raindrops, and there'll be a lot of lightning and rainfall. And then the lightning will start. Then the rainfall will start to dissipate, and the air will cool. Okay. So again, average annual lightning flashes per square kilometer. A very interesting map here of the world. And again, you look at the lightning flashes here over Florida, it gets very close to the reddish area. Okay, so it kind of mimics the area with the thunderstorms. So lightning, is there always a thunderstorm when there's lightning? Not necessarily, but there's quite a correlation between thunderstorms and lightning in this map. Okay, tornadoes, local storm of short duration, features a violent windstorm, rotating column of air that extends down from a cumulonimbus cloud. Low pressure inside causes the air to rush into the tornado. Winds approach 300 miles per hour. Smaller suction vortices can form inside stronger tornadoes. Okay, there's an average of 770 each year in the United States, most frequent from April to June. Associated with severe thunderstorms that cause a tornado formation is not known. Conditions for the formation of tornadoes, though, occur mostly along the cold front during spring months, associated with huge thunderstorms called supercells. Okay, the characteristics would be 150 to 600 meters, so about 500 to 2,000 feet in diameter, so they're nowhere near as large as a hurricane. Speed across the landscape at about 30 miles per hour. Cut about 6 miles long path. Most move towards the northeast. The maximum winds range beyond 310 miles per hour. Intensity is measured by the Fujitsu intensity scale. Okay, so average annual tornado incidence for a 27 period. Okay, so average, so let's see, right where we are, we're somewhere around 5 to 6 tornadoes on average per year where we are. Over here in Oklahoma, they're averaging 9 tornadoes per year on average. Okay, so here's our tornadoes versus tornado days per month. Okay, so we see that April, May, and June we have amount of tornadoes rising. Here's the peak of tornadoes, mostly between April, May, and June, and then we'll have less in July and August. Okay, paths now in Illinois from 1916 to 1969. They've mapped the paths of major tornadoes. So here, the tornadoes that are along the ground are those red arrows, and the length of the arrow this is the path that tornado traveled. This one traveled a very long way. Many tornadoes traveled shorter distances. Tornado forecasting. It's difficult to forecast because of their small size. We don't really have the constant monitoring at a scale to be able to pick up smaller featured objects in large fronts. So we use a tornado watch to alert the public of possibility of tornadoes when certain conditions are favorable. Then alerts will go out to let people know that there's a chance of a tornado, and we'll cover 25,000 square miles. Tornado warnings issued when a tornado is actually sighted or is indicated by weather radar. The use of Doppler radar helps increase accuracy by detecting the air motion. Here's a picture of a tornado. And here's a picture of tornado damage. Okay, so the enhanced intensity scale, an EF0 tornado, from 65 to 85 miles per hour, so like a Cat 1 hurricane. Some damage, okay, but it goes up to, let's say, EF2, so over 100 to 135. So we're still in the hurricane ranges, miles per hour. We've had some house damage here. But let's say EF4, now we're talking 166 to 200 miles per hour, so faster than our hurricanes. Devastating damage, complete destruction of well-built residences and large sections of school buildings, for example. EF5, greater than 200 miles per hour, so incredible amounts of damage, significant structural deformation of mid and high-rise buildings, so serious damage. Now hurricanes, here's a picture of a typical hurricane with its eye, wind spiraling out. Okay, so hurricanes are the most violent storms on Earth. To be called a hurricane, the wind speed needs to be greater than 74 miles per hour. It's rotary cyclonic circulation. They form between latitudes of 5 degrees and 20 degrees latitude. And I think we're just over 20. We're probably about 22, 23 degrees latitude where we are. Hurricanes are known as typhoons in the Western Pacific and cyclones in the Indian Ocean. North Pacific has the greatest number per year. Parts of a hurricane, they have an eye wall, which is near the center, the rising air, intense convective activity. And the eye wall is a wall of cumulonimbus clouds, greatest high wind speeds, heaviest rainfall. This is where you can find some tornadoes, anticyclonic tornadoes. So right in that eye wall is the most dangerous activity. The eye is the very center, often on average about 12 miles in diameter. So where precipitation ceases, winds subside, air gradually descends and is heated by compression. It's the warmest part of the storm. So here's a cross-section. So here we have the eye where there's sinking air. So our winds die down, precipitation stops just in that middle of the eye. But the eye wall itself is the fastest part of that hurricane. So the eye wall crosses the path. Winds will pick up greatly. So there's outflow, there's spiraling wind bands here. Here's another picture of another large hurricane. So this hurricane is larger than Florida. And these hurricanes are really large storms. Wind speeds can reach up to 300 kilometers per hour, generate up to 50-foot waves at sea. Now hurricanes form in all tropical waters except the South Atlantic and eastern South Pacific. Energy comes from condensing water vapor, developed most often in late summer when warm water temperatures provide energy and moisture. The peak of hurricane season for us is 2 weeks before Labor Day through 2 weeks after Labor Day. Initial stage is not well understood, but typically a tropical depression is the beginning of one, where winds aren't more than 38 miles per hour. Then a tropical storm, we have 38 to 75 miles per hour winds. Hurricanes will decay when they move over cooler ocean water. When they move on to land, but they don't seem to die very quickly and move on to Florida. Usually you move on to land, you picture there's a topographic difference, and especially that land mass is very dry, sucks some of the energy right out of it. Large-scale flow aloft is unfavorable, so sometimes you'll find that pressure systems that will that the hurricane doesn't like, basically will weaken that hurricane. So here we have a weather map. So this is Hurricane Fran, 1996. So you see how the low pressure here, how steep that pressure gradient is. That means the winds are going to be really fast. Okay, so as this hurricane's traveling, this is Thursday, and then by Friday, so it makes landfall over here in the Carolinas, and then by the next day, it's up over Virginia, and it's now weakened. You can see the isobars are farther apart. It's now just a tropical storm. Strength. Okay. Also, how this what affects destruction of a hurricane? How much damage we get? Well, the strength of the storm is the most important factor. Also, size and population density of the area affected, and the shape of the ocean bottom near the shore. The Saffir-Simpson scale ranks the relative intensities of hurricanes. So, a Cat 1 hurricanes are weakest one at 74 miles per hour. Cat 2's at 96. Cat 3's at 111. Cat 4's at 131, and Cat 5 is 156 or greater wind speeds. And that's our catastrophic storms. The storm surges associated average like 18 feet for Cat 5, 13 feet for 4, 9 for 3, 6 for a 2, and 4 for a 1. This is highly variable depending on the shape of the ocean floor. You might have a larger storm surge in the Gulf of Mexico with a gentle slope to the ocean floor there. The East Coast is much steeper and would have possibly less storm surge. So the storm surge is actually a large dome of water, 40 to 50 miles wide. Basically, the hurricane's pushing the water, so it's doming up, and it goes across the coast where the eye makes landfall. Then you also have wind damage on top of that, and then inland flooding from torrential rains. Okay, so here we have a hurricane that's traveling at 50 kilometers per hour. Okay. The winds, okay, are 125 kilometers, okay, going this way. So on this side of the storm's traveling this way, and the wind's going this way. So you kind of add up, so the travel speed's 50 kilometers plus 125. Okay, so the wind is actually traveling, so basically 175 kilometer winds on this side. But here the winds are traveling this way, so you'd subtract out the forward speed from the wind speed. So the net result is 125 kilometer winds in this way. Okay, here is an example of a hurricane map, Tropical Storm Dean from 2007. So here's where the tropical storm is here. And this is just a prediction. So here, this is all the area where the storm might be in the next 1 to 3 days, somewhere in here. And then over here, the next 4 to 5 days. Okay? They're saying it's going to be a storm, and then about 4 days out, it's going to turn to a hurricane. Now, this line here doesn't mean anything. Okay? This line has actually gotten some trouble in the past. People assume, they look at this, oh, the hurricane's going to follow this line. Well, actually, that storm could be anywhere in this cone, anywhere. That line is just to make it easier to show where, where the map's going and a place to put the S's and the H's. That line has no greater prediction value than the rest of this polygon here.